Welcome to The Explainer. Today, we're going to pull back the curtain on the invisible world of signals and systems, the hidden language that, believe it or not, powers pretty much everything in our modern lives.
So let's just start with something we all take for granted. You make a phone call. Have you ever stopped to really think about how your voice, your actual voice, can travel thousands of miles in less than a second?
You speak into your phone and boom, someone on the other side of the planet hears you. It really does feel like magic. But the answer isn't a magic trick. It's the incredible science of signals and systems, the true unsung hero of our totally connected world. To really get how this all works, we first need to get to know the star of the show, and that is, of course, the signal. So, what is a signal when you strip it all down? Well, at its very core, it's just a carrier of information. It could be the sound waves from your voice, the light coming from your TV screen, or the electrical pulses zipping through a cable. It's the message itself. And if you could actually see a signal, it would often look something like this, like a wave. Its ups and downs, its shape, its frequency, that's not random. The shape of the wave is the information.
Okay, so a signal is the message. But a message is pretty useless if there's no one to carry it or understand it, right? Well, that's where systems come into play.
A system is like a translator or a messenger. It takes a signal in, it does something to it, maybe it amplifies it, filters out noise, or changes it completely, and then it sends out a brand new signal on the other side. Your phone is the perfect example. It's a brilliant little system that takes the input signal, your voice, and processes it into a powerful output signal that can actually make that journey across the globe. Now, this is where it gets really cool. To build great systems, engineers have to understand the personality of a signal. They have to know its characteristics. You can think of it like decoding a signal's DNA.
So first up, we can ask a simple question. Is the signal a smooth, continuous wave like a flowing river, or is it broken up into a series of individual little snapshots like a connect-the-dots puzzle?
And here you can see the difference perfectly. On the left, that's a continuous signal. Think of the sound wave coming off an old-school vinyl record. It's one unbroken, smooth groove. On the right, that's a discrete signal. It's more like a digital MP3 file, which is really just a series of thousands of tiny samples of the original sound. Okay, next question we can ask about our signal is, can we predict what it's going to do next? Is it totally predictable, like the steady tick-tock of a clock? Or is it completely random and unpredictable, like the static you hear between radio stations? The signal on the left you can see follows a clear mathematical pattern. You know exactly where it's going. The one on the right, though, that's pure chaos. That could be anything from stock market changes to the noise in an electrical circuit. You have absolutely no idea what's coming next.
Absolutely. And you know what? Some signals have this beautiful, almost artistic symmetry to them, which actually turns out to be incredibly useful for processing them.
An even signal is basically a perfect mirror image of itself. If you put a mirror right on that vertical axis, what happens on one side is the exact reflection of what happens on the other. This simple rectangular pulse is a great classic example of an even signal. See how the left half is a perfect mirror image of the right half? It's perfectly balanced. Now an odd signal, that's a little bit different. With an odd signal, it's like you take the right side, flip it over the horizontal axis first, and then it becomes a mirror image of the left side. A classic sine wave is the perfect example of an odd signal.
But what about signals that just repeat themselves over and over and over again? You know, like the rhythm of a song or the beating of a heart. Well, we call those periodic signals. This sine wave is a perfect periodic signal, and that interval there, labeled T0, that's what engineers call the fundamental period. It tells us exactly how often that pattern repeats itself.
All right, last one, I promise. We can also classify signals based on their oomph. Some signals are like a clap of thunder. They have a finite, measurable amount of energy that's released in a burst. Others, they're more like the steady hum of your refrigerator. They have a continuous, finite power that just keeps on going. And here's the key takeaway on this one. A signal can be an energy signal or a power signal, but it can never be both. Think of it like this. An energy signal is a burst, and a power signal is a steady stream. You're either one or the other. So, okay, we've got all these labels: continuous, discrete, even, odd, energy, power. Why does any of this matter? Why do we need to classify them? Well, let's connect all the dots
and see how this stuff truly shapes our entire world.
These concepts, they are the invisible engine behind almost all of our modern technology. Your phone works by converting the continuous signal of your voice into a discrete one. Your Wi-Fi router, it's a system designed specifically to filter out random noise so it can focus on the periodic data signal you care about. From medical imaging like MRIs to listening for signals from deep space, it is all built on this language.
So, the next time you make a phone call, or stream a video, or even just send a simple text, remember the incredible journey your voice and your data are taking. It's all happening thanks to the power of signals and systems, the hidden language of our world. And now you know how to speak it.